Good. So let's get started. Well, the first thing I want to talk about is the homework, actually. So if you haven't done that, so I'm sure most of you haven't done that as we approach the end of the term. So I can see that only a handful of you have attempted the homework. Well, I cannot force you, okay? So after all, they don't count into the final grade, but it's important, let me say it again, to actually catch up with all the nuance, especially, which there's a lot in this course, about how to attempt the question. And this exercise really helps you to do that, okay? So you can see that in recent exercise, I try to incorporate some exam questions, which is from the previous course, time series. That course actually has a number of overlapping topics with this time series course, okay? So those questions should really be helpful in prepare you to prepare for the ST418 exam in May or June. I think it should be June. Yeah. Okay. So again, if you have any questions when you attempt the exercise or exam questions, let me know. Okay. You can post it on the discussion forum or just jot me an email. Okay. No problem. Okay. Then, so let me see. Last week, we were talking about the factor model. So we spent, I think, most of the time on granular causality. So granular causality concept is not difficult, but we talked about the equivalence of one of the definition with another. So you need to be able to prove that equivalence, as I said in the last lecture. And then we started the topic of really dimension reduction, okay? And we focus on factor modeling. There are lots of dimension reduction methods, but we focus on this multi-factor model, which we have started in the latter half of the last lecture. So we talk about this meaning of the factor model, okay? So it's basically to explain a lot of dynamics. So let's say look at this equation 5.38 in the lecture notes. So it's basically to explain the dynamics of this factor RT. So let's consider that as so I'm going to use again a finance example. So let's consider this as all the FTSE 100 stocks. Okay, so FTSE 100 is on the low these 3 weeks, but anyway, so FTSE 100 stocks return. Now I talked about return before. Okay, so it's basically the difference of lot prices. And then, well, there are hundreds of them. Now, you don't really want to use any of the multivariate model we talked about to model this. Because, let's say, a vector armor model, so you need a lot of parameters, okay? In particular, every coefficient matrix will be 100 times hundreds, which is 10,000, okay? 10,000 different parameters, and that's one coefficient matrix. You may have several, okay? So you don't really want to do that, especially with these limited data. When I say limited, you may argue, well, I can easily download 10 years, 20 years data, right? But look at the model here. The premise is we assume the dynamics stays constant like this. The dynamics is a constant mean alpha plus a certain multiplication structure of a vector loading matrix times certain unknown latent dynamics. And that loading matrix B You see, it's not dependent on time. So if you download 30 years, no problem, but are you sure that this equation 5.38 is gonna stay valid for the whole duration of your data? That's very questionable, okay? So in order to make it more realistic, usually people, at least I'm saying in finance or economics, usually people just talk about maybe half a year, 1 year, or at most 2 years, okay? So they don't want to look at too long time frame unless their model is truly adaptive to time changes. There are a lot of these models, but it's out of scope of this course, okay? So for this kind of structure, factor loading matrix stays time independent, and all these are additive structure. So all this fixed structure over time, so we want our time horizon to be as short as possible to really be more robust to the change, okay? So we hope that this structure is valid throughout the time of our data, the duration of our data. Okay, so this factor loading matrix is basically the same number of rows as the response factor. So if we are talking about FTSE 100, then there will be 100 rows in this B. But how many columns? Well, the number of columns is much reduced. The number of columns is, I use R to denote that. So here, I use capital K. In my handwritten note, I use R, so here I use capital K. So K here is the number of unknown or latent factors, okay? And so B is of dimension P times K, okay? P is usually much, much larger than K. So let's say K maybe just 1 or 2. So in something so-called capital asset pricing model or CAPM, so if you have learned this from other classes, so K is goes to 1. So it's just basically one factor model. So B is not a matrix, B is a factor in terms of a capital asset pricing model. Okay. Well, in economics, maybe people want a little bit more nuance in the changes. Maybe one factor is not enough. One factor usually is the market factor in terms of financial returns. So maybe some more, maybe sector, or maybe some other kind of factors that is related to stock characteristics. Okay, so if you're interested in these kind of things, so look no further than the Farmer and French website. So you can Google it, really. So Farmer and French, so they have a dedicated websites. They run a lot of their constructed portfolios. Even matrix portfolios, so we will talk about that in their website, okay? So they're 3 or 5 factor model, something like that. And so these are really important, okay, to understand. So why do we need dimension reduction, okay? Because in the end, all this RT can be modeled by just the factors FT. So FT actually affects all the dynamics of RT. So if FT is only one scalar in a CAPM, usually the market factor, so let's say FTSE 100, then FT usually is the what? The FTSE 100 index, okay? So it's basically a summary of all the performances of all the 100 stocks. Then of course this market index will be important in explaining all different 100 stocks dynamics, okay? So that's the dimension reduction. So we give it meaning. And the additive structure, well, of course, and the multiplicative structure in this, of course, yeah, you can say maybe it's kind of restrictive, but here, remember, our only observed factor is RT. So we basically decompose into something that is unknown, okay? So even if you decompose into something that is wildly nonlinear, in the end maybe is not as good as just decomposing it linearly into this kind of thing, okay? Because after all these are unknown, okay? Alpha, B, Ft, all these are unknown parameters, basically. Okay, so I've talked about this enough. How do we estimate this? So last time we just introduced this factor model. And how do we estimate this model? And before that, so I'll also introduce another kind of motivation for dimension reduction. Okay. So let's start off with talking about the covariance matrix. Of the response factor. So the response factor, what I was talking about, of course, is the, let's use xt here. Okay, this is alpha plus b times ft plus epsilon t. Okay. Let's say you observe t from 1 to capital T, the sample size. Okay. So how do we estimate these parameters? Well, beforehand, let's look at the covariance matrix. If we assume that, which is usually the assumptions, the covariance matrix between your Ft and epsilon t is 0. Well, is it a restrictive assumption? Well, kind of, but remember, again, all these parameters on the right-hand side are estimated, okay? So this assumption is merely basically assigning information. You're basically assigning information so that the noise is uncorrelated with the factors Ft. Now, what will happen if we assume this Ft and epsilon t are uncorrelated? Then the covariance matrix, which is defined as the variance of xt. Of course, variance of xt is the variance covariance matrix, or I just say covariance matrix. Usually I skip the variance part. Okay. So when I say covariance matrix or a factor, I mean the variance covariance matrix. So it's the variance of, first of all, alpha is a constant. So variance of a constant, of course, you can ignore that. So what you're left with is just Bft plus epsilon t. Now, using the assumption Ft and epsilon t equals to 0, the covariance between them, then this variance, of course, can be split into just the sum of the variance of these two components. Remember the name of these two components in factor model jargon. Okay, so Bft is the common component. Epsilon t is the idiosyncratic noise. Okay. So when you say this, everyone knows that you're talking about factor model and referring to what component. So common component, idiosyncratic noise is all in the lecture notes. So how do we expand this? Variance of Bft is B times variance of Ft times B transpose, okay? And then plus variance of epsilon t. So let's define it as variance of Ft, let's define it as sigma f. And variance of epsilon t, let's define it as variance of epsilon, as sigma epsilon. So they're all stationary, basically, time independent. Now, so what's so special? Why do we look at this sigma? Well, the first thing I want you to notice is, so now the sigma, the variance covariance matrix, is now a sum of two parts, okay? So suppose further that the sigma epsilon is diagonal, so if we assume sigma epsilon is diagonal, what does it mean? So all the epsilon t's are uncorrelated. So idiosyncratic noise of different response corresponding to different response are uncorrelated. So all the potential correlation among the C100 stocks are actually contained in the factors itself. Without the factors, they are uncorrelated. That's what it means by this assumption. Sigma epsilon is diagonal. So again, all the correlation of these 100 stocks, they are correlated, well, because it's driven by one dynamic, the Ft. So without this Ft, the noise is actually uncorrelated. Okay, so that's what we assume here, if sigma epsilon is diagonal. So usually, when we talk about something called a straight factor model, so this is basically a straight factor model. Straight in the sense that all the factors contain all the information about the correlation amongst these different stocks or these different response variables. Okay? And the total number of unknowns in B is actually, I use D, right? So xt is a d-dimensional factor. So if xt is a d-dimensional factor, then B is actually d times R. So R is the number of factors, okay? And then in sigma R, in sigma F is R times R plus 1 divided by 2, right? It's R by R matrix and it's symmetric, okay? So if you count it, it will be R times R plus 1 divided by 2. And we assume sigma epsilon is diagonal, so it's just D, okay? So what am I doing? I'm just showing you just total number of unknowns parameters. Is dr plus d plus r times r plus 1 divided by 2. And then if you compare with an unstructured factor xt, if variance of xt, if xt is unstructured, if there's not a factor model to model the dynamics of xt, then sigma potentially has what? Potentially of course it's dimension d times d plus 1 divided by 2. Let's say if these are 100, then it's 5,000, around 5,000 or 5,050 number of parameters in sigma. But let's say if you're using a cap M, a capital SM pricing model R equals to 1, then it's just 200 plus 1, right? Yeah. So 200 plus 1, 201 number of parameters compared to over 5,000 parameters. Okay, so it's a huge dimension reduction. When your concern is the covariance matrix. And if you think about it, so you're all master students, so covariance matrix is basically how we do statistical inference and methodologies, right? Covariance matrix is all the information that we always use, okay? So with this kind of dimension reduction, this all kind of inferences are much easier to do, estimation inferences, okay? And therefore people prefer this kind of factor model for huge dimension reduction, okay? So the meaning is in the factor model itself, but also it implies that the variance covariance matrix has a huge dimension reduction. And sigma being equals to this, so people will call it low rank plus, this is diagonal, but usually when people try to say, okay, maybe not exactly diagonal, but a lot of zeros. Most of them are zeros, but maybe some of them are non-zero, okay? So it's a sparse matrix rather than an exactly diagonal matrix, okay? So you must have, maybe you have heard it, people talk about these things, right? What is low rank plus sparse? Right? When people say low rank plus sparse, they're talking about the covariance matrix implied by a factor model, okay? So they are talking about factor model, basically. So why is it low rank? So this is low rank because B is just a D by R matrix. Sigma F is an R by R matrix. So the rank is on at most R. And R is small, so low rank, okay? And this is a sparse matrix. Of course, we assume this, but conceptually, it should be true, okay? So most of the covariance is taken away by the common dynamics Ft, common factors Ft. So after taking away the common dynamics, most of the residuals are uncorrelated, but maybe some of them are correlated still. Maybe if you include two stocks that are very closely related together, okay, so maybe something in the same sector, maybe Ford, Tesla, okay, perhaps they follow some bad news or good news at the same time, okay. So it's basically that maybe a sector factor that is ignored in here, and the residual may be related, maybe correlated, okay, for stocks within the same sector. Other than that, well, most of the epsilons are reasonably to be assumed to be uncorrelated. So I hope I explained clear what this factor model means and why do we do some of the assumptions. Sigma epsilon is diagonal, sigma epsilon is sparse here, and the implication of this formula for the variance covariance matrix for the observed variable xt. Okay, so any questions? Use some time to explain all of these. Okay, now let's go to the part that helps you solve this week exercise. Well, if you have looked at that, okay, so this week exercise actually involves estimation of a factor model, which I haven't talked about until now. Okay. So we'll talk about estimation, not inferences. So inferences, I think, is quite complicated actually. So let's write down the model again. I'll use B. So let's suppose your sample size is T, capital T. So what you have as data, let me remind you again, so you just observe this. X1 up to X capital T. That's it. That's all you observe. So how to estimate all these, okay? Well, certainly your model is not identifiable. Whenever your model involves two unknowns multiplied together, certainly they are not identifiable. For instance, if your matrix H is invertible, then this happens. So if you assume a dash, use B. So B dash is B times H, and then Ft dash to be H inverse times Ft. Then what happens is B dash times Ft dash is exactly BFT. That means they give the same model, okay? So giving the same model. So it's not identifiable, certainly. So we need to give some restrictions on the parameters. So how do you do that? Well, by the way, there's something called the factor loading space, which I will not test you, but conceptually, this is defined as the span of the columns in B. So this is some linear algebra notation. So even if the exact B and Ft, they are not identifiable, so even in this model, the span of B is uniquely defined, okay? The span of B means the column space of the matrix B, okay? So imagine the factors, the column factors in B. You take all kind of linear combination of B, all possible linear combination of the columns in B. and they will form a vector space, okay? And that space is the span of B, okay? This is the vector loading space. This vector loading space is actually uniquely defined. No matter what H you use, it will result in the same vector loading space, okay? So ultimately, it's actually the vector loading space we are interested in. Okay. So let me at least give a definition of span of B. So B is the set of all vectors formed by the linear combinations of the columns in B, okay? So no matter what H you use, this space remains the same, okay? No matter what invertible H you use, it will be the same span, the same vector space. So it's this space that we are interested in. And if we want to estimate one matrix B, so people will say it's only a version of the matrix B that represents the same vector space span of B. So even if it's not unique, maybe it's not that important. So as long as you have a version of an estimator that belongs to the span of B, then perhaps it's fine, okay? But people still restrict the B such that it is having orthonormal columns. So R is number of factors, of course. And it's assumed no. So this assumption means that B has orthonormal columns, right? So B transpose B is the identity matrix. That means each column is unit vectors, first thing. And then identity matrix, that means all the off diagonals are 0. The off diagonals are the dot product of different columns. So the dot product of different columns, they are 0. That means all the factors are orthogonal to each other. They are orthogonal, each are unit vectors, that means they are orthonormal columns. So say 1 here, maybe. That's the first restriction, and then the second restriction will assume also the sum of ft is 0. So the first restriction, basically, both restrictions basically facilitate a unique solution, okay? A unique solution. Well, as long as we have a unique solution, so B is a version of the possible B that represent the span of the vector loading space, okay? The true vector loading space. So this model is still unidentifiable. If H is orthogonal, that means H transpose is H transpose H. It's identity matrix, then well, BH transpose times BH is equals to what? Is H transpose BH. And with that restriction 1, B transpose is identity, so it's H transpose H, so it's still identity matrix. So even with restriction 1 is, well, it's still unidentifiable, but orthogonal matrix multiplied to the columns of B, that means a rotation. Okay, so it's basically a version of B is the a certain rotation of the columns of B. Okay, these are all linear algebra jargon. Okay, so the most important thing is remember how these two restrictions facilitate the solution, which I am going to talk about now. So let me continue, and let me start with a new page. So how do we really solve this? So we use least square estimation. So how is it done? Well, the model is, remember, xt equals to alpha plus bft plus epsilon t. So consider a function to be minimized, which is q alpha, b, and f. I'll explain what f is. So which is sum from 1 to capital T, our sample size. Well, of the norm of the epsilon t's, right? The epsilon t's are xt minus alpha minus b times ft. That's a proper least square setup, right? And what is f here? Well, f is basically just putting all the f1 up to ft into a matrix. Okay, so f1, f2, dot, 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 up to ft as a matrix. So f is basically r times t. And we have to incorporate our restriction. So that means what? That means B transpose B is the identity matrix, and F bar is 0. F bar is the sum of the FT divided by T, so this is 0. So least square estimation with the two restrictions incorporated. So you need to know how to solve this, so I'll solve this together with you. So to minimize Q, there's an order of solving these different parameters in terms of other parameters that made the question much easier. So perhaps you can see that the first thing you want to eliminate is maybe alpha. Alpha is the easiest to estimate. Well, consider dq alpha. Well, wait a minute. So Q is, of course, a scalar. Okay, sum of the norm of square, so it's a scalar. But alpha is a vector, so we're talking about multivariate differentiation here. Okay, so I can't remember if I have taught any multivariate differentiation, but in statistics, there are usually only two rules you need to know for multivariate differentiation. First rule, so alpha, the dot product as a scalar, if you differentiate with respect to one of the variable, what happens is what you left with is the other, okay? So all these factors are column factors, okay? They're always column factors. So if you differentiate W transpose alpha with respect to alpha, what you get is not W transpose just, but W. Okay? This is the same as differentiation of W transpose alpha, D alpha. Alpha transpose W, W transpose alpha, they're the same, okay? So that's the first rule. And then the second rule, differentiation of quadratic forms. So alpha transpose A alpha, so again a scalar. So this is quadratic form. So what do you think it will be? So a little bit more complicated than your one variable counterpart. So it will be this. And therefore, if A is symmetric, this differential will be equals to 2A alpha. 2A alpha is kind of your expectation, right? This alpha transpose alpha is basically in scalar is like A alpha square, right? Differentiate with respect to alpha, of course, is 2A alpha. A little bit more complicated than that, but if A is symmetric, then it really goes back to 2A alpha. So it's basically a generalization of your very basic differentiation rule, but upgraded to a multivariate case. So all you need to know is only these two, okay? So what is dq d alpha then? Well, what is norm square? Look at the top of the page. So that's norm square. Norm square is the transpose times itself, right? So let me write it like this. Okay. So if you expand this, well, there's certain terms that relate to alpha, okay? So the summation doesn't matter, so let's write it outside. And then differentiation of the inside. Well, how do you do that? Well, it's basically the product. Okay, so all the chain rules kind of apply. So, or product rule. So you differentiate with respect to the first term first, and then differentiate this term with respect to alpha. So that's the product rule, right? And then you differentiate the second term with respect to itself, and then differentiate the inside with respect to alpha, okay? So I will let you verify in the end that this is minus 2 times xt minus alpha minus aft. So what we're basically doing is similar to, okay, we drop this 2 in front and then differentiate alpha with minus alpha with respect to alpha, that's minus 1, okay? So really it's just like scalar differentiation in this case, in this particular case. But you can verify the exact validity of this using these 2 rules of differentiation, okay? So if this is 0, then what is your alpha? Well, look at this. So minus 2 can be taken to the left-hand side, so that's 0. So the sum of xt, t from 1 to capital T, and then minus, I've already taken minus 2 out, so, and then minus alpha, minus t alpha actually, and then minus, this should be b, sorry. So write a and then it follows here. So this should be b that we're estimating, and then minus b times the sum of ft, right? And this is the first restriction. Now this is 0, okay? But the second restriction actually. And that means what? That means alpha is just x bar. So basically, you're saying that, so your ft, if it has mean 0, then alpha should have the mean for the xt, which of course makes sense, right? So ft doesn't contain any mean information, sum of ft is 0. Then the mean should be really alpha, okay? So alpha is x bar. So that's how the second restriction makes this one way simpler. So I said the exercise is exactly for you to redo all this, okay? So you have to know how to do this. It would seem to do for a long time, very complicated, but because I'm just explaining this, okay? So it shouldn't be too difficult, to be honest. So hence, we can modify Q alpha AF to be what? So it's just QAF equals to the sum of xt minus x bar minus BFT. Yeah? I use A again, so BFT. And this should be expanded now to make it easier for us to differentiate. So let's put a bracket here. Xt minus x bar, of course, comes together very naturally. So that means the mean version of xt. And how do you expand this? Well, I hope you get used to this very quickly. So it's basically a plus b all squared is a squared plus 2ab plus b squared, right? But it's a factor version. Well, factor version is very similar. So it's minus 2 times. So 2ab becomes 2a dot b. Okay, so it's a transpose times the BFT. And then plus b square is the norm square, okay? So norm of BFT square. So it equals to, well, xt minus x bar doesn't depend on any parameters, but this does, so it's minus 2 times. Let's write it in terms of the transpose, so ft transpose b transpose times xt minus x bar. And then plus, what is norm of BFT? Well, is using the definition is ft transpose B transpose B times ft, right? And B transpose B is the identity, so it will be just ft transpose ft. So here, if you differentiate with respect to each ft, so let me be a little bit less ambiguous. I differentiate with fs, okay? So the time unit is s. We have f1 up to f capital T, but now we differentiate with fs. And that is what, fs? Well, we have some t from 1 to t, okay? Each ft are variables, okay? And now we differentiate with fs, okay, so fs, right? So there's only the fs term that is to be differentiated here. All others will be 0, okay? So what is left? So the summation disappears because all variables will be differentiated exactly to 0. They are treated like constant, except the s term. Xt minus x bar norm square, well, doesn't depend on any parameters, it's differentiated to 0. Now, how about this second term? 2fs transpose b transpose xs minus x bar. Well, using the first rule of differentiation, okay. So first rule, so this is a dot product of ft times b transpose xt minus x bar. So what you're left with is just this. So the easiest mistake you can make is it becomes minus 2 xt minus x bar times transpose times b, okay? So if you look at that, even the dimension is not right. So differentiate the scalar with respect to fs, so it should be still an r-dimensional vector. B transpose times xt minus x bar is exactly an r-dimensional vector. But xt minus x bar transpose times b, well, it's not, okay? So, and then plus the differential of ft transpose ft with respect to ft. Well, that's the second rule. It's a quadratic form with the matrix A in between equals to the identity. So it's 2 times the identity times ft. I used t again, so it should be s actually. And I've differentiated this, so what you're left with is this. So the differentiation is completed like this. So it implies that if we set this to 0, what do we have? So you can immediately see that, so Fs will equals to what? It equals to B transpose times XS minus X bar, okay? So bear with me, give me maybe 3 more minutes. So that's the last part, okay? So we got alpha, we got F in terms of the final parameter, which is the factor loading matrix B, okay? So now we finally and further modify Q to Q of B, which is the sum T from 1 to capital T. Again, something that doesn't matter in the end. Norm of xt minus x bar squared minus 2 ft transpose B transpose. Now F is this, right? So substitute this into here. Okay, so minus 2 times xt minus x bar transpose times B. That's ft transpose, and then B transpose times xt minus x bar. And then plus, well, ft transpose ft. So it's just direct substitution. So plus ft transpose ft is substitute with B transpose xt minus x bar. But these two it's minus 2 of this plus 1 of this, so it's minus 1 of that. Okay. So ultimately this is T from 1 to capital T, xt minus x bar all squared minus the sum of xt minus x bar transpose times B, B transpose xt minus x bar. Alright. Give me 2 more minutes. So we are minimizing Q of B, right? Minimizing Q of B is equivalent to maximizing the term which is being minused here, being subtracted here. So it's equivalent to maximizing over B of this sum. And this sum equals to look at this sum. This sum is a scalar. Of course, it's a scalar. So this scalar is equivalent to, of course, the trace of the scalar itself. A scalar is the trace of the scalar itself. I introduced a trace in last lecture. Trace is the sum of the diagonal elements of any square matrix. A scalar is a 1 by 1 square matrix. So it itself is a trace of itself. And yeah, so obvious. So why do I do that then? Well, because trace of AB is trace of BA, remember? So now I can reverse the order of multiplication with the help of this trace. So it becomes B transpose times xt minus x bar times xt minus x bar transpose times B. Well, what's the use of that? The use of that is I finally can take the summation inside and make the whole problem much simpler. what is sigma x tilde? Sigma x tilde is the sample covariance matrix. It's basically multiplied with t, of course. So it's t inverse sum of t from 1 to t, xt minus x bar times xt minus x bar transpose. This is exactly the sample covariance matrix of the original data you observed. So finally, the problem becomes maximize of this trace of B transpose times the sample covariance matrix of your data times B. And remember, B has to be having all column vectors, which are unit vectors. And they're orthogonal to each other. And this setting exactly facilitates the solution. Or you need to make sense, or you need to maybe remember this kind of problem. So it means that B can be taken as the first R eigenvectors of the matrix in between, which is here the sample covariance matrix for the data X. If that sounds familiar, this is exactly solution for PCA, right? Principal component analysis. Principal component analysis of your data actually coincide with your estimation of a factor model. Okay, so you need to know how to prove this. Okay, so that is the whole proof. When I say first R eigenvectors is corresponding to the first largest R eigenvalues, of course. Okay, so that's it. So that's all the solution, and run over a little bit. So here, let me give you 10 minutes, okay? 10 minutes break, a little bit longer, because I want you to take some time to complete the survey for the course. If you haven't completed the survey of the course, so let me remind you by sending you a reminder email. So I know that some of you are still copying, so I'll give you maybe 2 more minutes. So you should have received earlier emails about different courses for their survey. So let me send you the link again. So let me see if I can do that. Very quickly. So just ask the system to send you a reminder of the course survey. So please do take some time to finish the course survey. So I'll give you 10 minutes starting from now. So go back to .com if you haven't completed the copying. Let me show you the full page. So please try to complete the survey. Okay, so in order that this is a small class, in order that we have enough data to talk about performance. So we resume at 219. So this, I'm going to talk about this numerical results. Okay, so let's resume our lecture. So I hope you will have time later, or if not now, to finish the survey. So we'll just take care of a little bit more of this estimation, and that's it. So the main estimator, we are done, because the factor loading matrix will be basically the PCA of the sigma x tilde. So therefore, B hat is obtained by principal component analysis of the sample data matrix, and take the first R eigenvectors. First R eigenvectors means it corresponds to the first R largest eigenvalues, okay? So as explained above. And then there are other estimators, so we can substitute back. So what is your FT? So your FT hat is B hat transpose times XT minus X bar. So therefore, finally, of course, your alpha hat is X bar. But what is your epsilon T hat then? Well, epsilon T hat, of course, is just XT minus alpha hat, which is X bar, and then minus B hat times FT hat. So of course we have all these estimators. And we also can estimate our variance covariance matrix, which is a very important input in a lot of statistical methods. So if we assume our factor model, then it will be B hat times sigma tilde F hat times B hat transpose, and then plus sigma hat epsilon, where what is the sigma tilde F hat is just the sample covariance matrix, of the F hat. Okay. So I don't need to center the FT hat because it's already centered, right? We assume it's centered basically when we are solving them. Now at the same time, so sigma epsilon hat. For straight factor model, it will be a diagonal matrix, right? Diagonal matrix of the sample covariance matrix for the epsilon t hat. That is a straight factor model. If it's now, how about you can ask how about sparse matrix? Well, sparse matrix, then you need to maybe threshold this matrix. So a certain value lower than a preset value in the matrix, then it will be set to 0. If it's above certain preset value, then the U is left as it is. That's one way. There are other ways, so I will not go into details of those other ways. If you're interested in this kind of thing, so large covariance matrix estimation, factor model, so I've introduced a paper in the lecture notes, so you can have a look at that. Okay. In there, so it talks about exactly a low rank plus sparse covariance matrix for the residuals, for the idiosyncratic noise. Okay. So so it seems pretty done and closed. Well, except one thing. So I assume the number of factors is known. So how do we know the number of factors? Okay, so we just assume it's R and then go on with it. So how do we know R? Well, I don't need you to know exactly how to find R. I just need you to know the practical method. Okay. So the practical thing is, in general, for a factor model, with all factors, which are all pervasive. Remember pervasiveness, right? So I assume all factors are affecting all the dynamics of all the time series units you have observed. Then there are large eigenvalues, usually of order D. Of the sample covariance matrix for your observation. And the rest are relatively smaller. Most of the time, it doesn't really have too clear cut of what large and small is. So here, basically imply that we need to estimate sigma by your sample covariance matrix, sigma tilde x. And then first look at the eigenvalues. Of sigma tilde x. Perhaps plot from largest to smallest. And we have a name for this thing. So if you have done PCA, so you should know the name. This is called a squeak plot, right? This is exactly PCA, okay? So maybe you already know this. So if we see our large eigenvalues, and the rest are relatively smaller, then we use R as the number of factors. There are estimators that can be proved to be consistent estimator, but depending on your purpose, most of the purposes for doing this factor model, people would rather overestimate the number of factors. Okay, you really don't want to underestimate in all statistical procedures that I can think of, but overestimate, most of them is fine if you don't overestimate too much. Okay, so for instance, if you have true number of factors is say 2, maybe you overestimate by 1 or 2, it is fine. But if you underestimate, then it's serious. Okay, you're seriously wrong about any estimation, any statistical procedures that follows. Okay, overestimation not usually a big problem. Okay, so that's the practical side of it. Let me show you one example that is in the lecture notes. So let me run this with you. So let me go to the PC. So in the So in the lecture notes, it is example 5.2. So we have daily return of 100 portfolios. So these portfolios are constructed according to some calculated fundamentals of a stock. Okay, so you can actually look at the the data here. This is, by the way, the Farmer and French web page already. Okay, so they form many different portfolios. This is 100 portfolios constructed using, well, size and book to market ratio. Okay, yeah, they have explained what kind of stocks are there. So these are MISC stocks, AMEX stocks, NASDAQ stocks, etc., etc. Okay, so my aim is to look at these 100 stocks and see if I can do dimensional reduction using a factor model. Okay, so the data can actually be downloaded here. So 10 by 10 portfolios by size and book to market ratio. This is exactly the data that I can download. So if you look at all the R scripts, there is also one portfolio.r. Now the portfolios.r is with respect to this example. This example runs elsewhere as well. So when we teach about the matrix factor model later on in the final lecture, so this will still be used. But for now, let's look at this script corresponding these 100 portfolios. Okay, so they are actually weekly data, so I need to take care of this weekly nature of the data. So this lubricate data, if you look at what library lubricate is, it's basically to take care of, in particular, weekly data, okay, so that you can analyze them as usual. Okay, so you may ask what's so special about weekly data that you need a particular package to take care of it. Okay, well, I will not explain too much, but there are nuances that weekly data gives to our code. Okay, I don't know if Python or MATLAB will suffer the same thing, but at least R will. Okay. So at the end of the day, we constructed this array of data. So if you look at the size of size is MATLAB again. Sorry about that. Size is MATLAB. So R is dim. Okay, so dimension. So this is 100 times 2,515. 100, of course, is the 100 portfolio. So row represent the dimension, and then the columns represent the sample size. Okay, so you have a sample size of around 10 years of data. So 10 years of running this 100 portfolios. All right, and each of them should be a return. Okay, so and we run a gauge model. You see, a gauge 1-1 model basically for each time series first. So each row represents the time series, right? We want a gauge 1-1 model to fit the return for each time series first, and then we standardize them. Okay, standardize means we take the residual of this gauge 1-1 fit. If you remember, so gauge 1-1 fit's residual is exactly the normalized return. So we take this residual of gauge 1-1 fit of each row of data as the normalized return for each row. Okay, and then put it back to the p dot array as the data. Okay, so after gauge 1-1 fit, the first data will not be available, so we remove them. Okay, so with this, we put it back to a 10 by 10 matrix. Originally, it's given to us as a 10 by 10 matrix. There are 100 portfolios, but it's given to us as a 10 by 10 matrix. Okay, so we plot the first 4 sizes. So let's plot this. I don't know if it's large enough, so maybe it needs to be really large window. Okay, so I think this corresponds to what we have plotted in the lecture notes. So in the lecture notes, I think I plot the same thing on page 87. Yes, here. I think it's exactly the same plot. Okay. So what I want you to see here is, of course, it's very difficult to see, but hopefully, factor model is suitable for describing this 16. I'm plotting 16, but there are hundreds, of course. Okay, so 16 of them. Do they look similar in the sense that they can be described by a lower dimensional dynamics? So perhaps. So some of them look at these 3. So the 3 of them are affected by a spike in the same time, 2020. Okay, as with many others as well, actually. So it's really difficult to see. So how about directly finding the number of factors? If we want to find the number of factors, it means we're doing PCA. So PCA in R is done by printcom, okay, the command. So if you do this PCA and plot the square plot, so this is the square plot actually. So how many factors are there? Well, you can say it's just 1. You see, 1 is way above the others. That's usually indication of a very dominant factor which is common in a financial time series case, is the market factor, right? There's always a market factor. And then the second and third, maybe, second and fourth, it really is very similar to the others. And the second and third, well, the intensity is much smaller as well. They are not exactly very small, but compared to the first one, the magnitude is much smaller. Okay, it usually means that perhaps there indeed are the second and third factors, but these second and third factors may be affecting only a handful of stocks rather than all of the stocks. Here, these are the portfolios, okay? Maybe only affecting maybe 10% of the portfolios, 20%, but not all of them. The first factor, obviously, is affecting perhaps almost all 100 different portfolios, okay? All right. So perhaps you may say one factor, but as I said before, you usually prefer to overestimate the number of factors for most of your procedures, okay? So perhaps you can take three, okay? Three factors. So that's what I took, I think. So that's all these practical consideration of estimation of a factor model and estimation of number of factors, okay? So that's all you need to know. Any questions? So as I said in this lecture note, so of course there are many papers about estimation of these things, okay? And but this particular example is actually given to us as a matrix of time series rather than a factor of 100 portfolios, okay? So we will look at them as a matrix of time series later on, okay? So if you don't have any questions, so that's good. So we move on to our final topic, okay? So with what I've taught, you should be able to do all the exercise now. So have a try and try to catch up with all the exercise before the final week. So we're approaching the last topic. Well, the last topic, as you can see in the lecture notes, so is matrix time series. A matrix factor model. Well, in a lot of more traditional, let's say econometrics courses, so maybe at this stage they'll talk about state space model, Kalman filter, okay? So I skip all this. First of all, Kalman filter, because I haven't even introduced spectral density or filtering in that aspect, so I'll skip that. As well as this matrix and time series matrix factor model is getting more important over the past decade, and that's why I choose to at least talk about this, okay? And how people deal with this kind of matrix data. There are lots of different situations that arise from this matrix data. The easiest is what I'm going to talk about, the matrix factor model, still a dimension reduction, okay? And many others, for instance, I don't know if you heard of the partial least square. Partial least square is basically finding the largest correlation between a response variable and predictor variables, okay? So in one dimension, so partial least square is basically for forecasting. So it's very traditional forecasting method. So not many people look at them with proof properties, but I think in 2015 there's a Journal of Econometrics paper that looked at that very seriously and provide influential results. Okay, but that's for factor observations. So how about matrix time series? Okay, so matrix time series, is there a way to talk about a matrix of response variable and perhaps even larger matrix of predictor variables? So how can we talk about their correlation? Well, of course, you can factorize all of them and talk about correlation, as a matrix, but you lose some inherent matrix structure. So let me write the notation, and then I'll explain along the way. Okay. So your time series, of course, notation is xt. So your xt is not a scalar anymore. It's not a factor, but it's a matrix. Let's say it's a P times Q matrix. So let's say we have x1t, x2t, and all the way up to xqt. Okay. So there are q different columns. Each column is actually a p-dimensional vector. Okay. So one of the examples, well, there are lots of examples. For instance, if we talk about the portfolio example we just look at, is given to us as a 10 by 10 matrix time series, actually. So it's 10 different size of portfolios across 10 different books to market ratio. Okay, so each column represents a 1 book to market ratio. Okay, so x1t perhaps represent a book to market ratio that is extremely small, and then the elements in it are different sizes. Okay, x2t maybe not as small as the first one, still different sizes in its elements. Okay, and all the way up to xqt. So the q book to market ratio. In the previous example, q equals to 10 as well. Okay, so 10 different book to market ratio give us 10 different factors. Each factor also of dimension 10, so it's 10 by 10, right? In the end, 10 by 10 different, 100 different portfolios. And in a lot of economics data, so for instance, if you are given, for instance, row usually represent different countries, and columns usually represent different micro or macroeconomic indicators. For instance, maybe you're looking at all the G7 countries. Okay, so each xit will be of dimension 7, and q is 1. Well, perhaps you're looking at the GDP, well, consumer price index, well, PPI, etc. Okay, so all these different macroeconomic indicators. So it can be really huge if you look at a lot of them. All right. Let's forget about any potential of missing values. Okay, so let's not talk about that. That will really complicate things. Okay. So there are a lot of examples, even just in economics and finance. Okay. So and apparently, so different countries, and then across different micro or macroeconomic time series, this certainly look like it has an inherent matrix structure in it. So if you no one can stop you from stacking the columns of X. So one way is to stack the columns of xt to form this flag of xt. Equals to, let's say xt, which is x1t, x2t, all the way up to xqt. So as a column factor, a really long column factor. So it is a p times q dimensional column factor. So no one can stop you from doing this, and then find, okay, let's find a factor model for this bold xt, which is a pq dimensional random factor. Okay, so different countries, different macroeconomic indicators all stacked together to form a really long factor. When you can do that, well, the first problem is a dimension problem. So dimension now is p times q, right? It could turn out dimension pq can be too large. Compared to sample size t. Well, depend on your purpose, okay? So if you want to do more complicated inference for a factor model, then certainly PQ cannot be too much larger than T. For accurate estimation of a factor model. Factor model is what we just talked about in the first half of the lecture for xt. Let's say your sample size is, well, if we were talking about economic data, maybe 200, 300 is a lot already for economic data. But PQ can be, if P is 20, Q is 30, P times Q is what? Well, 600, okay? Well, still not too much larger than the sample size, but as soon as it's getting larger than the sample size, estimation accuracy starts to reduce. Depending on what you estimate, again, but I'm not going into detail of those, okay? So, but this in general is true. So something, some estimators' estimation accuracy will be reduced when your dimension of the factor is too large. This matrix time series factor usually comes in P not too large, Q not too large compared to the sample size, but P times Q certainly will be much larger than T. So this poses a dimensional problem, very practical problem. At the same time, your xt usually is presented with a matrix structure, an inherent structure. The countries by economic indicators example is very natural of a matrix structure, okay? So usually the countries by economic indicators. So stacking really loses the natural matrix structure. So if you want a factor model running through this matrix time series, you really want to retain the structure, so as to retain the interpretation, so to speak. Okay. Now stacking, then so different countries, different economic indicators for another country. Well, they all stack together. Okay. You know, so the natural interpretation with a matrix structure is lost. Okay. So I think I will have enough time next week to talk about starting from the matrix factor model to the end. Okay, so I will stop it here. So next week we'll talk about the matrix factor model for this matrix time series. Okay, which is the last topic of the course. All right. So I will see you guys next week. Remember to complete the survey if you haven't, okay? So there's not a lot of people responding, so hopefully it will improve. How was the presentation? I know. I just know this afternoon. They haven't promoted it, so.
Yeah. I nearly submitted a PowerPoint like that. It's good. I can show you the PowerPoint.
So have you done any numerical results to show?
Yeah. I literally run the simulation. Was it in the current market? Yeah, it looks covered. For large
He is good while he declared last city. I can't say that. No, last year, because he did all the pure courses.
Yeah,
I haven't proved it.
Yeah.
Interesting, and why 49 or 50? So it has to be less than T. What?
79.
Okay.
And why 49 is like to form the wave matrix.
Oh, I
it has to be
understand.
the
I understand. Yeah, it should be. It should be rectangular. It's square.
have to.
So.
I mean, like I have.
For now, it's okay.
For some of that,
And the behavior should, as it should be. Yeah. If we are doing the
Oh,
first
no.
paper, then maybe
this is
one more.
So I went by
The electricity is 400, and they just want to see that you
I have.
women's wear
So,
agree
I could do
with
both, but I also think that I have like no plans.
So two may not be.
It's kind of like because
So already
last summer I did an internship as
No, I can do more.
No, it's good.
Because it's genuinely this company.
It's good.
But
So in the end, you have to restrict
restrict
some of the squares.
I don't know.
During in the estimation section, I do
Well, we're in July. Were you guys talking about this in previous calls? Like, not really a topic of conversation.
doing the last
I think it is really medical actually.
I do the
Even fuel prices in the UK,
exactly
the highest since May 2024.
improve the gas price.
And the countries don't have
I see.
fertilizers.
The code.
Well, like have low stocks of fertilizers. Like fertilizers needed to plant crops. So crops harvest, like you plant crops.
Do they have any particular questions?
Yeah, the first question is why to choose the constraint?
Like everything.
Sounds weird.
Everything.
Maybe, as opposed to why not some,
Like
Yeah.
obviously,
I suppose.
who's the most
Second question is
most of them just stay there. Most of the
well, I estimate I estimate the coefficient, the weight of the women other than estimate the whole.
Oh, okay.